Hello, welcome to another module in this massive open online course on massive open online course. All right, and we are looking at the power spectral density of the transmitted digital communication signal. Okay, and we have derived the autocorrelation of the digital communication signal as follows: expected value of xt into xt plus tau. We have shown this is basically your Rxx of tau. We have shown that this is equal to that Rxx of tau is equal to Pd over T, where Pd is the power of the data symbols T is the symbol duration, T is the symbol duration, okay, times R Pt Pt of tau, where this is your autocorrelation of pulse Ptt. Okay. In fact, for any pulse p, this will simply be R Pp of tau. We can use any pulse tau. We do not need to be necessarily, we can use any pulse p, all right, Pt. We do not need to be necessarily limited to the rectangular pulse Pt, okay, P sub capital T, okay, all right, that was simply an example, okay, for instance. And now we also know that this R Pp of tau is, of course, this has Fourier transform. This is basically your R Pp of tau, which is autocorrelation of pulse Pt, is defined as minus infinity to infinity integral Pt minus tau dt, okay, this is R Pt tau. And if I take the Fourier transform of R Pt tau, okay, I obtain S Pp of f, correct, S Pp of f, which is the Fourier transform, that is Fourier transform of R Pp tau, which is R Pp tau integral minus infinity to infinity R Pp tau e to the power of minus j 2 pi f tau d tau. So, S Pp f, this is the Fourier transform of R Pp tau, and this can be shown to be, interestingly, we can show that S Pp f is equal to magnitude of Pf square, correct, magnitude of Pf square, where Pf is the Fourier transform of pulse Pt. Fourier transform of pulse Pt, that is what we mean is Pf equals integral minus infinity to infinity Pt e to the power of minus j 2 pi f t dt, and therefore, this is magnitude of Pf square, where Pf is the Fourier transform of the pulse Pt, and therefore, this quantity S Pp of f, this quantity is termed as the energy spectral density. or simply the ESD, energy spectral density of pulse PT, which is the Fourier transform, the autocorrelation function of the pulse PT. Okay. And therefore, what we have is we have the autocorrelation of the digital communication signal equals PD over T times the autocorrelation of the pulse RPP. If we take the Fourier transform on the left to get the, okay, we know that the power spectral density SXX of F equals minus infinity to infinity R XX tau e to the power of minus j 2 pi for a wide sense stationary process, correct. Power spectral density is given by the Fourier transform of the autocorrelation function for a, and this is an important property, for a wide sense stationary process, the power spectral density PSD is given by Fourier transform Fourier transform of the autocorrelation function. And therefore, what we have is we have, well, Sxx of f, which is the Fourier transform of Rxx tau, is equal to PD over T times the Fourier transform of Rpp tau, which is autocorrelation of the pulse. Okay. So, that is your S, you can call that as your Fourier transform of the autocorrelation SPP of f. But SPP of f is nothing but the energy spectral density, alright. This is the Fourier transform, the autocorrelation of the pulse, which is the energy spectral density, and therefore, we have this is equal to PD over T times magnitude of PF square. Okay. So, basically what we have is a very interesting result, that the power spectral density of the transmitted signal is proportional to energy spectral density of pulse. This is a very important result, that is the power spectral density of the transmitted digital communication signal is basically proportional to the energy spectral density of the pulse PT. Okay. So, this is an important property, okay, which helps us characterize what is the power, what is the spectral distribution of power of the transmitted digital communication signal, and what this result tells us is that it is nothing but a scaled version of the energy spectral density of the pulse. Okay. And now, for instance, let us take a simple example. Let us consider again, for the purpose of this example, consider the pulse PT equals the rectangular pulse. We are going back to our rectangular pulse, correct, which is our rectangular pulse zero to capital T, okay, or rectangular pulse 0 to capital T, or let us go back to our rectangular pulse the way we have defined it. Minus T by 2 to T by 2 for a height of 1, that is what we have defined the pulse to be, if you remember, correct. And now therefore, now this is our pulse Pt, this is the pulse, or rather this is our pulse P subscript capital T of t, and therefore, now if you look at the Fourier transform of this pulse, that is P subscript T of f is minus infinity to infinity P t of t e to the power of minus j 2 pi f t dt, and we have seen this pulse is nothing but this is equal to 1 if mod t less than equal to t by 2 and 0 otherwise, and this we have derived the Fourier transform of this already. This Fourier transform is t sinc f of t, which is equal to t sin pi f t divided by pi f t, and therefore, the magnitude P t f square equals, well, this is equal to T sinc f sinc square f t f t, which implies the power spectral density, the PSD equals, well, PD over T times magnitude Pt f square, which is equal to, well, Pd over T, I am sorry, this is T sinc f t, this is T square sinc square f t. So, this is times sinc square f t. So, this is Pd, well, Pd into T sinc square f t. Okay. So, this is the power spectral density of the transmitted signal. Okay. So, this is the this is the SXXF. This is your power spectral density. This is the power spectral density of the transmitted signal, okay. And thereby we have derived the expression for the power spectral density of this transmitted signal. Okay. So, that completes our analysis with respect to the power spectral density of the transmitted signal. Okay. And now, let us look at the properties of the digital communication channel. So, let us now proceed to look at the properties of a digital communication channel. So, let us look at the properties, or let us simply call this as the digital communication channel. How do we model a digital communication Now, simply put, the channel is the medium through which the transmitted signal propagates from the signal propagates or signal traverses from the transmitter to the receiver in a communication system. So, the channel is nothing but you can say it is the medium through which, or right, the medium through which the signal propagates from the transmitter to the receiver. Okay. So, channel, which is not very clearly defined in many contexts, it is simply you can think of it as a medium, because the transmitter and receiver are separated, medium through which signal propagates or signal travels from transmitter to receiver in a communication system, not necessarily a digital communication system only, in any communication system. For instance, in any communication system, correct, not necessarily. So, there is a channel, all right. So, in a communication system, by definition there is a transmitter, a receiver, and these are separated, all right. The transmitter transmits the signal which has to reach the receiver, the medium through which this signal propagates, correct, from the transmitter to receiver, that is termed as the channel. And there can be various kinds of channels. For instance, we can have some examples. Common examples are for instance your telephone lines, okay, coaxial cables which connect basically your set top boxes, okay. All right, coaxial cables which transmit, which are used for the transmission of TV signals, correct, or your cable basically, and also the wireless channel, all right, when there is no physical, when there is no particular guided propagation medium, when the electromagnetic waves are transmitted over the radio channel, over the air, right, for instance such as your AM, FM. In fact, this is turning out to be the most dominant mode of communication, that is for instance your all your broadcast services such as AM, FM, your cellular and all these things, cellular, Bluetooth, Wi-Fi, etc. all of these are based on the wireless channel, okay. Okay, when there is no particular physical a guided propagation medium, all right, it is simply transmitted over the air, all right, the radio channel, EM waves can propagate, of course, correct. And now therefore, we have our signal, correct, we have our transmitted signal which is xt equals summation k equals minus infinity to infinity a k p t minus k t, where capital T is the symbol time. Now, this signal x t, okay, we have this signal x t which traverses a channel, which passes through a channel, okay. So, this signal x t passes through a channel to the receiver and you have yt. So, this is the transmitted signal, this is your received signal, transmitted signal, received signal, and it passes through a channel. Now, one of the simplest models for a digital communication system or for any communication system for that matter is what is known as an additive white Gaussian noise channel, okay. One of the simplest, a simple communication system model. Now, a simple channel model is what is known as an additive white Gaussian noise channel, termed as an additive white Gaussian noise, AWGN. This is a very important, simple yet very important, where let me first explain what these different terms mean. A stands for, well, A stands for additive, W stands for white, G stands for Gaussian, and N stands for noise. So, this is basically an additive white Gaussian noise channel. So, AWGN basically represents an additive white Gaussian noise channel, which is one of the most prominent channel models, one of the most simplistic channel models employed to model the behavior, to understand the behavior, to model and understand the behavior and performance of communication systems, not just digital communication systems, but also for that matter any communication systems, also analog communication system and so on, okay, analog communication systems and so on. Okay. So, in an AWGN channel we have the received signal yt. It is a very simple model as I have described it, as I have said already, yt equals xt, received signal equals transmitted signal plus the noise. Okay. So, this is your received signal, we have already seen that. This is the transmitted signal. Transmitted signal and noise. In particular, look at this, this adds to the signal, this noise is additive in nature. The noise, this very symbol where the noise adds to the signal, noise. So, we have noise adds to signal. This is termed as this is a very important assumption that the noise is additive in nature. So, this is termed as additive noise. Okay. So, this is an additive noise channel, that is one of the important. So, in the name AWGN, where the phrase additive, right, the term additive means that the noise adds to the transmitted signal xt. Okay. All right. And of course, there are other aspects, that is the white and the Gaussian, all right, which need to be defined in order to complete the definition of the noise as well as the definition of this channel. So, we will look at these aspects in the next module. Okay. Thank you very much.